with your presentation. Here's your audience. Paul, please.
Thank you. Delighted to be here to really share just some ideas on how natural language processing can support geological modelling and mapping. It's a fast-moving space, natural language processing. These slides were produced a few days ago, so they're probably already out of date. But hopefully there'll be something that will be helpful. So talk a little bit about a conceptual model for natural language processing, how we can deal with unstructured information independently, but then also with the whole corpus. So all the literature, reports, information together, so the whole is greater than the sum of the parts, if you like. Focus on counting methods, the use of sentiment or tone, and then also vector space and summarize. So natural language processing, or NLP in short, is a branch of AI to really consider how computers can understand the written word and human language. I like to think of it as taking unstructured, sort of slightly disorganized information and making it structured in a way that we combine with existing measurement data and structured data. I'm going to talk about linguistic rules methods and machine learning, but it's not an either or. You can combine these methods, and often best solutions are a combination. So we can use things like regular expressions to extract information from unstructured data, part of speech tagging, domain linguistics, so taxonomies, reference data, ontologies, so identifying names of things in text through various methods, and then machine learning. So we can label data in sentences or paragraphs or whole documents to build a statistical model to then predict and generalize to find similar entities in unseen documents, which we know in generally almost every area there's far too much for a geoscientist to ever read. So we need some automated help. And then unsupervised machine learning, where in our language anyway, from left to right we have a sequence, but we can build using complex word co-occurrence a statistical model to predict for almost any word given any context what would be the following word, and we begin to move towards some of the language models that we all know and love and hate in different ways. So here's a conceptual model. So the first one is we've got some text here from a geoscience report. We can extract out concepts like lithostratigraphy, and these could be through taxonomies, they could be through a supervised machine learning model, and different other techniques. We've got chronostratigraphy there in yellow, as well as a geolocation and a quantity there, 100 meters thick, so it's numerical data. So we can extract this out in co-occurrence with each other. So where we have something in the same sentence or the same semantic structure, we can then make an association. And we can do that independently, so each document's separate to the others. The other is when we don't really care about the document, we put everything together and we start to look for patterns in amongst a large corpus of geoscience documents to surface some insights which are not really present in any single document. And it's a technique that's been used heavily in biosciences to discover new medical theories and products simply just by the volume of information that's being analysed. So here's a simple example. We've got like a mud log for a drill hole, and we're looking for casting or some sort of dissolution evidence. So we picked up vuggy there because we may have modelled it through taxonomies or ontologies, or maybe used some machine learning methods, and we've extracted it in association with the depth. So we've got a new data point, and we can plot that on seismic, we can integrate it in maps. And my general experience is a lot of geological process information is not stored in structured databases, and quite often it's not always incorporated in models. Sometimes when the volumes are too large, it's just never done. It's not a case of it being time consuming. So that might be a useful technique, just to use these automated, quite simple methods to extract that information. Here's another example, this time it's newspapers. So Lai et al. Looked at historical newspaper articles for evidence of flooding and georeferenced those by detecting place names and so forth in the data, which then can be integrated with risk reduction projects to inform local policies or regional or maybe even national policies when integrated with other data. This is an example of a summary, a stratigraphic summary from IHS, which is now S&P Global. And this is really just to illustrate that sometimes when we gather information together and then we summarize it, we can then miss out some information, just human error. Sometimes we just sort of smooth things out. So this is from the Gippsland Basin in Australia. These charts come with some PDF reports. So all I've done is run some NLP on these PDF reports just to show what may be missing from the chart. So, and I've just quoted the sentence that it's come from. So there's missing some, in this case, gas shows from the low Cretaceous, missing source rock up into the Eocene, and semi-regional seals in the upper Cretaceous. So this is just from a handful of PDF reports. So you can imagine if we gather together a large amount, it could well be that there's data hidden amongst, some people refer to it as dark data because it's hidden in amongst all this unstructured archives that, challenges what we think we know or what we think is a truth when we look at a summary or model. So the rest of the presentation, I'm going to focus on the whole corpus patterns through simple counting, through the sentiment, and then the vector space. Mainly in time and space, which are the two main contexts for geoscientists. So on your left is tweets. So this is so-called citizen science, where you've got people tweeting about flooding during a heavy rainstorm. And all it's done is it's got a frequency of the red are the high volumes of tweets, the blues and the greys are little to no tweets during that rainstorm, just to give, again, another source of data, sort of input into planning and perhaps environmental issues. And then on the right is from a collaboration with the British Geological Survey. There's something similar with earthquakes as well, which is detecting when people are tweeting around landslides, either through photographs or through text. And again, it's through NLP we can mine quite large data sources to extract out this additional data source. So sticking with the counting theme, but a little bit more complicated. So the histogram is 16 million censuses from the US Geological Survey. We've got Precambrian on the left, Pliocene on the right, and the black is the number of occurrences of evidence for source rock, this in the hydrocarbon sense. So it could mention source rock, or it could mention something like organic rich black shales. You can define out, say, through knowledge engineering, through machine learning, your semantic space, and it's just counting it. So it's visualized or summarized in a way, thousands of pieces of literature, but it hasn't smoothed out the outliers. So the dotted line is Clemian-Ulmschek's, rather elderly, but still valid in places, age of hydrocarbons in existing known fields. So you can see it's actually quite a reasonable correlation to the actual counts of the data from just the text, with a couple of exceptions. In the Silurian, we have far fewer counts than one would expect, and in the Eocene, we have far more than one would expect based on what we've discovered. So I'm not going to offer an explanation, but it's just an example of when we use these data-driven techniques on the literature to just surface these patterns, we can then use it to challenge our existing models, and where there are discrepancies or uncertainties, it could be an area for further investigation, further research, and so forth. The second plot is a bee-swarm chart, similar on geological literature, but on lithology. So we're detecting lithology clues. Again, we can use those knowledge engineering machine learning techniques. So we've got plastics there in yellow and blue in carbonate. And again, you're summarizing a large amount of literature, in some cases too much probably for being able to read. This is all on the Williston Basin. You could link that spatially to a map, which again could stimulate some ideas and thinking just based on the patterns of words and text. And then finally, we've got the sort of knowledge graph concept. So if you imagine a sentence, the Kimmeridge clay, it's Jurassic, you've got two concepts, two nodes, and the fact that they're in the same sentence or same semantic arrangement, we've got an edge, a link between them. And we can go through literature counting those and then generate a property graph where the links, the thickness of the line that you see in the visual is how many times it's come across that particular relationship. So we can see outliers and usual connections, and apply various graph algorithms to this to compare different areas through their connectedness of geological concepts. You can add, obviously, existing structured data and measurements in here as well. It doesn't have to be just generated from complex word co-occurrence patterns. And this is a similar concept, again, using USGS reports, but we're now using sentiment. So you can imagine when you found these concepts together, you have the tone of the sentence could be talking about something being immature or poor or rich or good. So we can come across or develop our own meaning of what it means to be positive or negative in a geological sense. If we use an out-of-the-box sentiment analyzer, whenever we come across any unit that says it's thick, we'll get negative sentiment. So we don't want to use an out-of-the-box sentiment. We want to create one that's geological. This one is speculation. The size of the pie chart we're looking here for clues for copper porphyry, is based on, the size is based on the level of speculation. So where the language is talking about possibly or might, or there's a question mark, some uncertainty, versus more objective where, this is a proven source, etc., etc. So you can use these different terms again to highlight areas that may warrant further investigation. So, a lot of text on this slide. So this is moving to vector space. So we can take sentences and turn them into numbers by using complex word co-occurrence. If we start simple with distributional semantics, it's been going on since the 1950s. A simple example I've got there is pegmatite, where we've gone through sentence after sentence, document after document, and just counted the words that are near pegmatite. So you've got tourmaline there in this fictitious example 34 times, biotite granite 29 times. So you imagine that this vector, we can almost semantically define what pegmatite is by the words that occur around it. We can then take vectors and using cosine similarity compare them. So the more similar two vectors are, then the closer they will be to one. And that can be quite a useful technique to show. And if we develop this further and we look at long-range dependency of words, parallel processing, vast amounts of content, weighted inputs, then we eventually get towards language models from vector space. And this is connecting with Mark's presentation. This is also from Lawley. They took a couple of 100,000 mineral reports, Natural Resources Canada, and clustered minerals just based on their word vectors. Then flattened it using principal component analysis. So you can see here where we've got a couple of minerals from disparate classification groups, scheelite and molybdenite, which could have some implications for porphyry scar mineral deposits. So data-driven discovery, just by the patterns of words in text. And these techniques have been around for quite a while. The Geo Deep Dive Initiative from the University of Wisconsin, I think, goes back to about 2014, 2015. And they've been running these sorts of techniques on millions of geoscience literature and have debunked some geological orthodoxies or theories about, particularly around in the area of paleontology, simply by looking at the literature, which it has provided more evidence than the theories that people had previously. So what I've done here is on the left is actual soil measure data on plagioclase compositions on the east coast of US. The picture on the right is nothing to do with soil measurements. It's purely the patterns of words in text, where we're using open source lists of place names and comparing the vectors to plagioclase. So where they're similar, you'll see that they'll be closer to red, and where they're dissimilar, they're in blue. So you can see there's, these are actually, unfortunately, two different map projections, so I tried to align them. But what you could do is actually compare them and end up with a sort of a contradiction or an uncertainty map where the word vectors don't match with the soil measurements. And this could be an interesting area to try and understand why that is. It could be data artifact. It could be something that is showing that maybe the measurements are incorrect or something else is going on. So lots of potential using word vectors, especially with large volumes of text. So finally, this is a project working with Geoscience World. They're a non-profit based in Washington, DC. They have a large chunk of the geoscientific literature. We're making this tool freely available towards the end of the year, and it's to search all of the literature, but rather than a search box and you just type in keywords, you get lists, you can interrogate it using word vectors. So here's an example where I'm comparing the Slanos Basin and the Picayance Basin. I want to look at lithology, 2D cross-plot. The Slanos Basin is on the x-axis, the Picayance is on the y-axis. So as lithologies plot further to the right, they're closer to the Slanos Basin. As they plot further to the top, they're closer to the Picayance Basin. And you can see some nice sort of clustering of how these two basins are different based on the patterns of words and text. And we've been testing it with research geoscientists, industry geoscientists, to sort of fine-tune that. But hopefully we'll support some idea generation. So in summary, NLP just useful for grabbing more data to input into our models, inputting social perception elements also into our models, connecting geoscience with the social elements. And then finally, just thinking of, that the whole is greater than some of the parts. By putting all of this information together, we have so much geoscience literature that there, may be new patterns in there that we can interpret and generate theories that could then become the orthodoxy for that field. So thanks for listening. Happy to take any questions.
So, thank you very much, Paul, for this very impressive talk. Interesting. I'm sure there are several questions on that. We don't have so much time, but there is now the opportunity to ask them. Yes, please.
Paul, how does that figure out when in a sentence the paper debunks something else? It's got the word plagiarism in it, but actually it's saying that Smith 1853 wrongly called it plagiarism. How does it deal with negative information if we are looking for words?
Yeah, so two pretty important NLP techniques is negation. So if you're looking for the evidence of something, hydrogen sulfide, you don't want to count there was no hydrogen sulfide. So that is a particular technique that you apply to the text when you run these techniques. The other would be word-sense disambiguation. So, just because you come across Paris, for example, doesn't mean you're talking about Paris in France. It could be Paris in the US. So there are lots of these techniques that need to be applied to ensure that you get the best accuracy with what you're modelling.
I get that. How do you get a negative sentiment? Not there was nothing there,
yeah.
But what you said was wrong. I'm disagreeing with another author.
Yes.
How does that sentiment get captured?
Well, you can model that. I mean, authors, often disagree with each other. So you can pick that up depending on how you model the sentiment. So the contradictions and disagreements can be, you can pick that up and just model it.
Yes, please.
Quick question on thanks for a very interesting talk and the overview here. The data, obviously, that you get big data sets, right? And a big success of foundation models was this huge scrape back, basically. In your case, you used now scientific literature partly in this last project you showed?
Yeah, so the geoscience world is over 4 million records. It's about 250,000 full journal papers. But yes, I mean, in an ideal world, we'd use everything that exists. But we
typically is the web scraping limitations that you have in journals and so on. But so for this data set, is this available for?
Yeah, I mean, the US Geological Survey is public domain, so most of what I showed was from the USGS. But yes, I mean, you can actually build models from different journals and compare that, or the difference between peer-reviewed versus non-peer-reviewed. I mean, the possibilities are horrendous.
Thanks for a great talk. I was particularly impressed by the way you map text to maps. So what Mark mentioned the spatial uncertainties in there. So how sure are you about the location of the dots and the labels when you do this mapping?
So I'm using an open source data set of place names and latitude, longitude. So I can't comment on the accuracy of those. And yeah, I mean, I think one thing that's interesting, not necessarily modelling mapping, but just from a search point of view, is that if someone types in chalcoporites or something like that, you can model it, but it will only ever give you the results that mention that. And I think that the value of using word vectors is that you can potentially highlight locations that don't actually mention what you're looking for, but because a lot of the other words are very similar, you could get a reasonably high similarity. So, that could be an interesting element, perhaps driven because it's indicator minerals or other indicator elements. But yes, I mean, the accuracy of the data set is like any other. Text has its own biases, and that will always be a limit on, what result comes out.
Yeah, unfortunately we don't have much time, so there's a question from you, and I will hog you at lunchtime with my question. Please.
Thinking about Christina's talk earlier, do you see national boundaries as priorities or geological training change? Or does it smooth out the boundaries beautiful, the borders?
Yeah, it's a good question. I don't have the evidence to say whether what would happen on that situation. But yes, it would be interesting to get a large amount of literature and then go across a border and see how the vectors would change. Indeed, yes. Thank you.
Thank you very much.